Multiprocessing is the use of two or more central processing units within a single computer system. The term also refers to the ability of a system to support more than one processor and/or the ability to allocate tasks between them. There are many variations on this basic theme, and the definition of multiprocessing can vary with context, mostly as a function of how CPUs are defined. According to some online dictionaries, a multiprocessor is a computer system having two or more processing units each sharing main memory and peripherals, in order to simultaneously process programs. A 2009 textbook defined multiprocessor system similarly, but noting that the processors may share some or all of the Systema Euro unregistered trademark S memory and I/O facilities. It also gave tightly coupled system as a synonymous term. At the operating system level, multiprocessing is sometimes used to refer to the execution of multiple concurrent processes in a system, with each process running on a separate CPU or core, as opposed to a single process at any one instant. When used with this definition, multiprocessing is sometimes contrasted with multitasking, which may use just a single processor but switch it in time slices between tasks. Multiprocessing, however, means true parallel execution of multiple processes using more than one processor. Multiprocessing doesn't necessarily mean that a single process or task uses more than one processor simultaneously. The term parallel processing is generally used to denote that scenario. Other authors prefer to refer to the operating system techniques as multiprogramming and reserve the term multiprocessing for the hardware aspect of having more than one processor. The remainder of this article discusses multiprocessing only in this hardware sense. In Flynn's taxonomy, multiprocessors as defined above are MIMD machines. As they are normally construed to be tightly coupled, multiprocessors are not the entire class of MIMD machines, which also contains message-passing multicomputer systems. Prehistory, according to a 1985 article in Byte, possibly the first expression of the idea of multiprocessing is found in the 1842 words of Luigi Federico Menabrea, which said about Charles Babbage's analytical engine, "The machine can be brought into play so as to give several results at the same time, which will greatly abridge the whole amount of the processes." Key topics. Processor symmetry in a multiprocessing system, all CPUs may be equal, or some may be reserved for special purposes. A combination of hardware and operating system software design considerations determine the symmetry in a given system. For example, hardware or software considerations may require that only one particular CPU respond to all hardware interrupts, whereas all other work in the system may be distributed equally among CPUs. Or execution of kernel mode code may be restricted to only one particular CPU, whereas user mode code may be executed in any combination of processors. Multiprocessing systems are often easier to design if such restrictions are imposed, but they tend to be less efficient than systems in which all CPUs are utilized. Systems that treat all CPUs equally are called symmetric multiprocessing systems. In systems where all CPUs are not equal, system resources may be divided in a number of ways, including asymmetric multiprocessing, non-uniform memory access multiprocessing, and clustered multiprocessing. Instruction and data streams In multiprocessing, the processors can be used to execute a single sequence of instructions in multiple contexts, multiple sequences of instructions in a single context, or multiple sequences of instructions in multiple contexts. Processor coupling Tightly coupled multiprocessor system. Tightly coupled multiprocessor systems contain multiple CPUs that are connected at the bus level. These CPUs may have access to a central shared memory, or may participate in a memory hierarchy with both local and shared memory, NUMA. The IBM P690 Regatta is an example of a high-end SMP system. Intel Xeon processors dominated the multiprocessor market for business PCs and were the only major x86 option until the release of AMD's Opteron range of processors in 2004. Both ranges of processors had their own board cache but provided access to shared memory. The Xeon processes via a common pipe and the Opteron processes via independent pathways to the system RAM. Chip multiprocessors, also known as multi-core computing, involves more than one processor placed on a single chip and can be thought of the most extreme form of tightly coupled multiprocessing. Mainframe systems with multiple processors are often tightly coupled. Loosely coupled multiprocessor system. Loosely coupled multiprocessor systems are based on multiple standalone single or dual processor commodity computers interconnected via a high-speed communication system. A Linux Beowulf cluster is an example of a loosely coupled system. Tightly coupled systems perform better and are physically smaller than loosely coupled systems, but have historically required greater initial investments and may depreciate rapidly. Nodes in a loosely coupled system are usually inexpensive commodity computers and can be recycled as independent machines upon retirement from the cluster. Power consumption is also a consideration. Tightly coupled systems tend to be much more energy efficient than clusters. This is because considerable economy can be realized by designing components to work together from the beginning in tightly coupled systems, whereas loosely coupled systems use components that were not necessarily intended specifically for use in such systems. Loosely coupled systems have the ability to run different operating systems or OS versions on different systems. Multiprocessor communication architecture equals message passing, separate address space for each processor. Processors communicate via message passing. Processors provide local message queue memories. Focus attention on costly non-local operations. Shared memory, processors communicate with shared address space. Processors communicate by memory read-write, easy on small-scale machines, lower latency, SMP or NUMA architecture. Flynn's taxonomy SISD multiprocessing equals in a single instruction stream, single data stream computer one processor sequentially processes instructions, each instruction processes one data item. One example is the von Neumann architecture with RISC. SIMD multiprocessing equals in a single instruction stream, multiple data stream computer one processor handles a stream of instructions, each one of which can perform calculations in parallel on multiple data locations. SIMD multiprocessing is well suited to parallel or vector processing, in which a very large set of data can be divided into parts that are individually subjected to identical but independent operations. A single instruction stream directs the operation of multiple processing units to perform the same manipulations simultaneously on potentially large amounts of data. For certain types of computing applications, this type of architecture can produce enormous increases in performance, in terms of the elapsed time required to complete a given task. However, a drawback to this architecture is that a large part of the system falls idle when programs or system tasks are executed that cannot be divided into units that can be processed in parallel. Additionally, programs must be carefully and specially written to take maximum advantage of the architecture, and often special optimizing compilers designed to produce code specifically for this environment must be used. Some compilers in this category provide special constructs or extensions to allow programmers to directly specify operations to be performed in parallel. SIMD multiprocessing finds wide use in certain domains such as computer simulation, but is of little use in general-purpose desktop and business computing environments. MISD multiprocessing equals MISD multiprocessing offers mainly the advantage of redundancy, since multiple processing units perform the same tasks on the same data, reducing the chances of incorrect results if one of the units fails. MISD architectures may involve comparisons between processing units to detect failures. Apart from the redundant and fail-safe character of this type of multiprocessing, it has few advantages, and it is very expensive. It does not improve performance. It can be implemented in a way that is transparent as software. It is used in array processors and is implemented in fault-tolerant machines. Another example of MISD is pipelined image processing, where every image pixel is piped through several hardware units performing several steps of image transformation. MIMD multiprocessing equals MIMD multiprocessing architecture is suitable for a wide variety of tasks in which completely independent and parallel execution of instructions touching different sets of data can be put to productive use. For this reason, and because it is easy to implement, MIMD predominates in multiprocessing. Processing is divided into multiple threads, each with its own hardware processor state, within a single software-defined process or within multiple processes. Insofar as a system has multiple threads awaiting dispatch, this architecture makes good use of hardware resources. MIMD does raise issues of deadlock and resource contention, however, since threads may collide in their access to resources in an unpredictable way that is difficult to manage efficiently. MIMD requires special coding in the operating system of a computer but does not require application changes unless the programs themselves use multiple threads. Both system and user software may need to use software constructs such as semaphores to prevent one thread from interfering with another if they should happen to cross paths in referencing the same data. This gating or locking process increases code complexity, lowers performance, and greatly increases the amount of testing required, although not usually enough to negate the advantages of multiprocessing. Similar conflicts can arise at the hardware level between processors, and must usually be resolved in hardware, or with a combination of software and hardware. See also, symmetric multiprocessing, asymmetric multiprocessing, multi-core processor, BMDFM, a Euro-binary modular data flow machine, an SMP-MIMD runtime environment, software lockout, OpenHMPP. References